Part 4 of our mock diploma exam. Starting on page 20 now, we're looking at multiple choice number 26. Look, we get a question like this, man. We got to nail this question. This is a gimme question, right? Guys, you remember that song? Radio Waves, Mike. I won't try to sing it for you here. If Bailey was here, maybe I would, but I won't. Which of the following lists has selected regions of the EM spectrum arranged in increasing photon energy? Increasing energy, same as increasing frequency, gentlemen. Same as increasing frequency. And when we have increasing frequency, we know that we go radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So it boils down to option B. Infrared, ultraviolet, X-rays, gamma rays. 27. Photoelectric effect. Here's our threshold frequency. This is not the frequency. This is the threshold frequency. This is the frequency. We want to find EK max. Let's say HF is equal to EK max plus the work function. And let's replace the work function with H times the threshold frequency. This is a real common question. Okay, this is a prototypical photoelectric effect question. I'm not suggesting that you'll see one exactly like this. You will see photoelectric effect for sure. But this is just the prototypical question, right? Where we use the equation that's not on our data sheet. We use the equation that's the most complicated. We end up replacing work function with H times the threshold frequency. Okay, this is a standard question right here. And not that hard of a question, actually. Want to find EK? Just rearrange it. Make sure you use the right value of Planck's constant. When you do that, it works out to be 1.7 times 10 to the minus 19. A. Yeah, go ahead. Yes, you can, but be careful with that, okay? Aiden's saying, if you didn't hear that, guys, could we just subtract the two frequencies and then say E is equal to H times F? Yes, that works. But the danger of that is this, okay? This equation is not delta E, H times delta F, okay? And that's what you did. You turned it into that equation. And that works here. And that works here because E and F are linear related. If it was F squared, which it's not, of course, then that wouldn't work. If it was H over F, that wouldn't work. If it was lambda, okay, you couldn't subtract the wavelengths and make that work because it's not a linear relationship. So honestly, Aiden, I'd probably stay away from that just because I think that can lead to mistakes in other places, not in this question, but in other places. All right, so I'd go this way. Okay. 28, the explanation of Compton effect requires the particle nature of light. Remember, photoelectric effect and the Compton effect were both particle theory. Photoelectric effect, Compton effect, the particle nature of light. We got, what do we have for the wave nature of light? We had polarization, refraction, diffraction, interference. So we got lots of things for both particle and wave theory. 29, one immediate result of the discovery of the cathode ray particles was that the theory of the atom was revised to a theory that was hypothesized that electrons, what do we got here? An atom contains negatively charged particles. All of these other things kind of, hey, they ring a bell for us. An indivisible sphere, that's Dalton, right? The Dalton solid sphere model of the atom. Probability clouds, that's the electron cloud model of the atom, the quantum mechanical model of the atom. Mostly empty space, that was Rutherford, the planetary model of the atom. Okay, this is the Thomson model of the atom. 30, an analysis of observations from Rutherford alpha. Notice they're not calling it the gold foil experiment. They like to call it, the diploma exam people like to call the gold foil experiment the Rutherford scattering experiment. Sorry, the alpha scattering experiment. It's the same thing. If you see these words here, don't get messed. Don't think, oh, what do I do? We haven't seen that. Yes, you have. We called it gold foil experiment. If they call it something different, don't worry about it. It led to a model of the atom in which the blank is in the order of 10 to the minus 10 meters in diameter, and the blank is in the order of 10 to the minus 15, and the majority of the blank is in the nucleus. Oh, boy. I'll tell you what, the third one is the easiest. It's the majority of the masses in the nucleus, right? It's like running into that 300-pound offensive lineman in the middle of the football field instead of the 2-year-old, right? Most of the mass is in the middle. Hey, but listen, I'll own up to this. I never told you anything about sizes, about numbers. Here's the good news is, probably no other physics teachers in the province told their students about numbers either. So how are you supposed to know this? Well, this is a smaller number. What's smaller, the atom or the nucleus? This is a bigger number. What's bigger, the atom or the nucleus? Well, the atom is bigger. The atom is in the order of 10 to the minus 10, and the nucleus is in the order of 10 to the minus 15. The answer is C. We don't have to memorize those numbers. Listen, I don't even have those numbers memorized, but I can answer the question because I know that the atom is bigger than the nucleus. That's all you got to know there. Everyone, hey, look, electron level diagram for mercury in electron volts. Notice the numbers are negative. Notice they're getting bigger as they get closer down to the nucleus. Notice that they're not evenly spaced. They never will be. Electrons on the 1.6 level, so the electron is right here. The minimum frequency to ionize it would be what? Well, to go up here, the energy is 0 minus 1.6, or 1.6 electron volts. We're going to set that equal to the h times the frequency. And we get 3.9 times 10 to the 14. Which two could we likely eliminate right away without even doing a single calculation there? C and D. Like 10 to the 33, 10 to the 34 hertz, way, 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 way too high there, right? Okay, 10 to the 15 could work. That's ultraviolet. That could work. Okay, it just doesn't work out here, but I would have said between A and B, 50-50 on that, right? For which of the following explanations did the diffraction of high-speed electrons provide experimental support? Guys, remember? Hey, de Broglie hypothesis. Remember, we said purely symmetrical argument, right? Physics is very symmetrical. Hey, if waves can behave like particles, then why can't particles behave like waves? And then evidence came from electron diffraction experiments. Remember that video we saw, the cartoon video, where the electrons are going through two openings at the same time, interfering with themselves, producing the interference patterns? That was evidence to support the de Broglie hypothesis. So we're going to say the answer is D for this. Okay, electron diffraction supports the de Broglie hypothesis. '33. Love these radioactivity questions. Love these transmutation questions because it's just like adding like simple numbers in our heads. Got a half-life, got a beta negative particle. Okay, let's draw attention to that, okay? Which of the following equations describes the decay of cobalt-60? Well, let's see. Going to be either this one or this one or this one, right? Beta negative. Let's just make sure those balance out. 60 plus 0 gives me 60. 28 plus negative 1 gives me 27. Same deal right here. What's the difference between A and B? We know it's not these ones, right? Because that's beta plus. Okay, it specifically says beta negative here. What's the difference between A and B? They look a lot the same to me. Neutrino, antineutrino, right? So which is it? Beta negative is neutrino or antineutrino? Antineutrino, so the answer would be B for this one. Percentage of cobalt-60 remaining after 15.6 years. Let's say N is equal to 15.6 over 5.2. The time over the half-life gives me 3. And then let's say, right, gentlemen? The amount that we start with is 100% since we're dealing with a percent. Do the math there. Works out to be 12.5. Or we're going to say, yeah, just write in 12.5.